We're going to explore here a few of the different interpretations of the derivative and try to get a feel for what they mean geometrically. And then we're going to, in number 4 and 5, we're going to use the numerical derivative features that we have on our calculator. First the nderiv, and then the dy dx that uses the graphing menu. And then we're going to look a little deeper and see that for some people this will be a rough day, that in fact sometimes the calculator will give us the wrong answer if we ask it to do certain derivatives. So that can be a bit shocking for people who have come to trust their calculator as a source of all truth and rightness in the world. But more importantly, we want to understand how the calculator computes its derivative, why that can lead to the incorrect answers sometimes, so that we know not to ask it to find the derivative in those situations where it's going to be incorrect. Okay, so first, it's kind of hard to read on this, but this little symbol up here is supposed to be an asterisk, meaning it's an unknown operation. So it is not a derivative, so it's not an f prime, but it's just naming this thing right here, which is really our difference quotient, f of x plus h minus f of x over h. So we're asked for a geometric interpretation, which means what does this mean in terms of a graph? So if we draw a little graph here, and here is our function, and we are going to say that here is the point x, and this then is the point f of x over here, and we go a little ways away from x, a distance of h away from x. That will bring us to an x value of x plus h, which when we plug x plus h into our function will in turn give us a y value of f of x plus h. So what we mean by f of x plus h minus f of x over h is this is in fact our slope formula. It's the average rate of change. So in terms of the graph, that means from these 2 points, x comma f of x and x plus h comma f of x, we are finding the slope of that line between those 2 points. So that's a slope formula, and it's the slope of what we call the secant line. So it's a line between 2 distinct points on a function. So that's what this first one is telling us. Then compare and contrast that now to the next one, which is, now this really is f prime of x, and notice it does have the limit where this one did not have a limit. So without the limit, this is an AP Prep or pre-calculus question. This with the limit now makes it a calculus problem. And so what we're finding now is to revisit the same function. I'm going to kind of sort of draw it the same. And we're still looking at this starting point of x comma f of x. So that's going to be the point x comma f of x. And we go away from that a little bit, h away from that, and we get a point whose coordinates are x plus h comma f of x plus h. Then we are starting with this difference between these two, looking at that slope. That's what this difference quotient is telling us. But now the difference is we're letting the limit go to 0. The limit is h goes to 0. So h, remember, is this distance that x plus h is from the x. So as that h goes to 0, we push this point along the line, and we're taking the, we can imagine, taking the slopes of those secant lines until we finally push that all the way to 0, and what we're getting is then the slope of that tangent line. So geometrically, what we're seeing is this is the slope of the tangent line, as opposed to what we saw in the first one was the slope of a secant line. Now the next one is kind of interesting, and see if we can try to understand the difference between what this is doing. So like before, we have our function f of x, and we are interested again in trying to find the slope of the tangent line at this point x. And what this is doing is, instead of like we did on the problem over here, where we started with this kind of anchor point, this place where we wanted to find the slope of the tangent line, we moved away a little bit and then we pushed that point closer and closer as h goes to 0. Here, what we're doing is we are taking values on either side of the place where we want to find the tangent line. So this expression, f of x plus h minus f of x minus h, I guess I should say, this x value is x plus h, making this y value f of x plus h. This is going to be the x value x minus h, making its y value f of x minus h. So what we're doing in this expression here, before we do the limit, is we're taking the slope of that line. Remember, we're trying to find the slope of the tangent line at x. We're taking a point the same distance on either side, and now at the same time, we're going to push these h's to 0. So as we do those various secant lines, eventually, if nothing goes wrong, we're still going to get that slope of the tangent line. Now, so that's the idea. Our calculator uses this without the limit to approximate its derivative, the numerical derivative, in the n-deriv feature. So what it does is not a limit, but f of x plus h minus f of x minus h all over 2h, but it just uses h equal to, I believe it's 1/1000th. So it will actually compute this, and that's just, of course, an approximation to the actual slope of the tangent line, but that is the result it's going to give us when we use n-deriv. Remarkably enough, most of the time, that is going to give us an answer that's going to be accurate to 3 decimal places, which is what we're trying to strive for, and actually, a lot of times, much more than 3 decimal places. The danger that we are going to see is this version of the derivative, or what our calculator is using as an approximation. Remember, this one is using the limit, which is going to be a true derivative. This one that our calculator does is only an approximation, but usually a very good one. The problem is it never tries to evaluate the function at that point where we are trying to find the tangent line. And that can be a problem sometimes, as we will see. So what we're going to do next here is on your calculator, we're going to be efficient, you might want to pause this, and you can put this function in as y1, and you can use that again for part B. For y2, you can say y2 equals, and do the absolute value of y1. That's what we're seeing right here. So to do the absolute value, you're going to hit your math button and then go right arrow to the numerical menu, and then that ABS is going to give you the absolute value. And I remind you to get to the y1 and y2, and we're going to do y3 and y4. You go to the variables button, VARS, just to the left of the clear button, go right arrow, hit enter, and then you're going to see all those options, y1, y2, y3. So before you actually start doing this, enter the function you see in A into y1. For C, you're going to go y2 equals absolute value of y1. Then you can enter this function as y3, and you can enter this function as y4. Now, once you have entered those in as y1, y2, y3, y4, now we can do the n-deriv part and evaluate these. So I'm going to stop this for a moment, and I'm going to write down what all of these answers are, and you can check them and see if you don't get the same things. Then we'll talk about how we're going to do number 5. So here are the answers that I got on my calculator when I used n-deriv at those places. So what we will do next, so we'll come back to that in a moment. Now we're going to move on to number 5, and now we're going to use the dy dx feature to do these same derivatives that we did in A, B, C, D, E, and F. So I'm going to write these answers here in red. But what we want to do now, when you go to graph this, when you see the y1 and you've got that entered and y2 and y3 and so on, these will all be the equal signs will all be highlighted initially. Now, if you hit the graph button now, it's going to graph all of these all at the same time, which is going to look like a crazy mess, and you'll have to try to sort out which one's which. Now, if you have a newer calculator and it's got colored graphs for each one, you can probably still get away with that. Otherwise, what I would do is move your cursor over to the equal sign, hit enter so that it's unhighlighted, leave only the first one you want to graph highlighted. So now when you hit the graph button, that one will show up, and you can go to the second trace, which is the calculate menu on your calculator, and go to the dy dx option. And then you can hit, once you get that on the screen, you can, for example, in part A, just type in -3, and it will enter that value in for x, and it will tell you what the dy dx is. And then you can write those down, and I'm going to write mine right next to these so we can compare them. Now, most of these are going to be the same, but surprisingly, not 100% of them. Then once you're finished with the first one here, then you can move your cursor left so it's on there, hit enter to unhighlight it, down arrow so that you're on top of the next one, hit enter to highlight that, and then you can find, that'll be the one for part C. You can do A and B off the same first graph. So I'm going to stop it here and write down my answers. You can pause it and you can do all those, and then we'll see if we don't get the same results. So here are my answers that I got when I plugged those in using the dy dx feature. Notice they all agree except at E, where on the dy dx option, it didn't give an answer. It said that the derivative doesn't exist. Curiously enough, that is actually the right answer, because if you notice when you factor that denominator, that the x's will cancel, which means there's a hole in the graph at x equals 0, which means the derivative doesn't exist there because the function is not continuous. That still leaves the x minus 1 in the denominator, which means there's a vertical asymptote at x equals 1, which means that this actually does not have a derivative. The derivative does not exist at x equals 1, and scarily enough, the 1,000,000 we got using nderiv is a wrong answer. And again, that goes to how it's trying to approximate this derivative numerically. Now, we will also find out eventually, surprisingly enough, that the derivative does not exist here either. So the answer 0 is incorrect. And I believe that the answer does not exist on this one either. We're going to get what's called a corner point. And I believe other than that, we're okay. Okay, so let's go on to the next page. We saw that when we used our calculator to find the derivative, both with the nderiv and also with the dy dx, it said the derivative was 0.0 a bit before. So as we come back here, the thing to notice is that the function, of course, this function is continuous, and there's no corner points, there's no vertical asymptotes, there's no cusp. So the derivative is going to exist at both of these points. So these values are correct, and we can have confidence in them. Where we get into trouble is where on this problem, these places where our parabola cross the x-axis, when we throw that into an absolute value, that's going to reflect that negative piece up, and it's going to create corner points there. And so at the point 2, and it would also happen at 1, then this derivative is not going to exist because we're trying to take the derivative at the corner point, but the calculator is not able to distinguish that. So we have to recognize where we might have a corner point and not try to take the derivative on our calculator there. And so here we got no problem. This we saw factored into x times x minus 1. This function has issues at x equals 0 and x equals positive 1. So the derivative will not exist at 0 because there's a hole in the graph there. It will not exist at x equals 1 because there's a vertical asymptote. Our calculator fails to see that and gives us an incorrect answer with n deriv. Now what we see at x minus 3 to the 2/3, and we're going to talk more about this in a moment, is that at 3, this is going to have a cusp. And so we talked about that a little before. The derivative does not exist at a cusp, but our calculator is giving us incorrect answers there. So here now, let me slide this down. We're okay. So what we're going to do now, we're going to try to get into this and look at this pencil and paper, not using the calculator. So our definition for absolute value, so we're looking at that second equation, the one with, or the third one, I believe, with the absolute value. And so when you have that absolute value of x squared minus 3x plus 2, then if you were to graph this, this is a parabola. This factors into x minus 2, x minus 1. So we can see that the parabola is going to open up and do something like this. So there's part of the parabola that is below the x-axis. Those are negative values of y. So the absolute value will take that negative part and reflect it up and make it positive. So the blue graph you see is the actual graph of y equals that absolute value. So what we're seeing is that there is a corner point at those places at x equals 1 and x equals 2, which means that the derivative doesn't exist there. But as we saw on the other page, our calculator gave us an answer there. So what we're going to do now is explore this further and look at pencil and paper how we should get that left-hand derivative and right-hand derivative at x equals 2. So the absolute value part says when x is positive, that's in this part of the graph here, then the absolute value just leaves it at face value x squared minus 3x plus 2. In this part where we see the green graph, that's where the parabola curve drops below the x-axis and becomes negative. The absolute value then multiplies it by -1 to move it to that blue graph there, which the blue graph is the actual absolute value graph. And so that's why we're getting this piece for the part that's between 1 and 2, that part of the green curve that was below the x-axis. So we're going to look at left-hand and right-hand derivatives at x equals 2. So we can use, we can take, so for our limit as x approaches 2 from the left, so our left-hand limit, that means we're going to use that second part of the branch there. And so we can do, let's do f of, and we're going to evaluate that at 2. So we're going to go 2 plus h minus f of 2 all over h. Now to get the limit as x approaches 2 from the left, actually let's do it this way. We're going to do it using our that alternative definition. So this one works particularly nice in this problem. So we're going to take the limit as x approaches 2 from the left of f of x minus f of 2 all over x minus 2. So this is our alternative definition of the derivative. So we're going to take again that limit as x approaches -2 or positive 2 rather from the left. So our f of x is going to be this negative x squared, And if I distribute that negative sign, plus 3x minus 2, and we're going to subtract from that f of 2, which is going to be a negative of 2 squared is 4, negative 3 times 2 is going to be a minus 6, and then we have the plus 2. And so that is going to be, I believe, 0 right there, still all over our x minus 2. So this is going to become, actually I'm going to leave it back in factored form, negative x squared minus 3x plus 2, because that's, I think, going to be a little easier to factor. So we're taking x as it approaches 2 from the left. If we plug in 2, we're going to get 0 over 0, which is indeterminate. So what we're going to do as we take that limit as x approaches 2 from the left is we're going to factor that x squared minus 3x plus 2 into x minus 2, x minus 1. We get to cancel these. That's what was causing that 0 over 0. So now we're going to take that limit as x approaches 2 from the left of negative quantity x minus 1. So we can direct substitute that 2 in. 2 minus 1 is 1. The negative of that makes that negative 1. So we're saying this is our left-hand limit, the limit as we approach 2 from the left. Now we're going to take the limit as we approach 2 from the right. So again, we're going to take this f of x minus f of 2 all over x minus 2. But now because we're coming in from the right, we're going to use this definition, this part of our f of x. So f of x is going to be x squared minus 3x plus 2 minus f of 2, which I think we said was 0, and all over the x minus 2. So this time, again, if you plug in the 2, we're going to get 0 over 0. Again, we're going to factor this, and then we're going to let x go to 2 from the right. So the x minus 2's cancel. We get x minus 1 as we take that limit as x approaches 2 from the right. We direct substitute in the 2. 2 minus 1 is 1. This is our right-hand limit. So what we're seeing is that our left-hand limit is not the same as our right-hand limit, and so therefore the limit does not exist. If the limit doesn't exist, that was our definition of the derivative. That means that f prime at 2 does not exist. This is disturbing because, as we saw on that other one. So here is an example of where the calculator is not giving us a correct answer. It's leading us astray. And again, the reason for that, and that's what we want to understand, is that when we go to evaluate it at this corner point, the calculator is not trying to actually do the definition of the derivative. It's using f of 2 minus plus 0.001 minus f at 2 minus 0.001 all over 0.002. And when you do that in this function, you're going to get that 0.001. But we know that is not correct. So going back to our calculator's answers to parts E and F, let's see what we know. And we talked about this. Okay, going back here. So that's what we're talking about in this problem here, where this thing has issues. Anywhere the derivative is not defined, our calculator can lead us astray. Now, in the next one, you should try doing this a little bit on your own and play around on a calculator, because it's kind of a nice little discovery thing. But what we're going to, the takeaway I'm going to go ahead and give you here, so you might want to pause it if you don't want to ruin the surprise. But what we want to know in the future, so that we don't get into trouble trying to use our calculator to evaluate a derivative where it's not going to be defined. But if if n is a positive integer, then x to the n will not have any corners. This is going to be just a nice power function, which is a nice simple polynomial, which means it's going to be continuous and differentiable everywhere. So this is continuous and differentiable everywhere. So that means there are no corners, also no cusps, no vertical tangents, no corners. And also, like I said, no cusp, no discontinuities, no vertical tangents. It's going to be differentiable everywhere. Now, to get a cusp, this takes some playing around, but what's going to happen is if we have x to an even over odd power, where this this exponent here is in between 0 and 1. So something like we saw on the other page, x to the 2/3 is going to be a cusp. X to the 4/5 will be a cusp. X to the 6/11, any even over odd, as long as this fraction is less than 1. So bigger than 0 and less than 1 is going to lead us to a graph that has a cusp. And for what values will this have a vertical tangent? It turns out this will be when we have x to the odd over odd power. And again, this is only going to be true when that exponent is between 0 and 1. So our classic example is the cube root function, but also something like 3/5 or x to whatever crazy odd numbers you could come up with. This will have a function that has a vertical tangent at 0. And then you can translate it. So something like x minus 2 to the 1/3 power is going to have a vertical tangent at x equals 2. So where will we have a restricted domain? Think like square root of x, 4th root of x, so on. So it's going to be an odd over an even, like to the 1/2, to the 1/4, so on. And again, where this is between 0 and 1. So our classic example is our square root. It has a restricted domain because you know that that square root function is only defined for x greater than or equal to 0. Its domain is restricted. Okay, very good.